All right, this is the intro video for AP Calculus BC, section 6.1, and this is focusing on a new topic, Euler's method. So Euler's method is a numerical approach to approximate the particular solution of a differential equation. This notation here might be a little bit new to you. All that really means is that y prime might be in terms of x or y or both. So I don't think that will, once you start to see these, I don't think that'll look too unique, but that notation might be a little bit unique. Okay, so again, I just want to emphasize what this is we are approximating a solution. So our answer will not be exact, but it'll be close, and really we can make it as close as we want by kind of manipulating what we'll later on call the step size. So this is an approximation, but it could be a very good approximation. It might be the best way to go in certain situations. So you'll be given some information. You'll be given an initial condition of the particular solution, as well as a little step value. The step value is usually labeled with the letter H, although it doesn't have to be. That's pretty common. So what we'll do is we'll start with the initial condition and use the step to approximate kind of the next point in the particular solution. And we'll use that point to approximate the next one, so on and so forth. And here is kind of an example of a cycle. What you're going to have is you're going to have x values, starting off with your initial condition, which is x0 and y0. And then you're just going to cycle through. You're going to find x1, x2, x3, to wherever we want to go. And the x's, you'll find the x's to be very easy to find typically. The y's will be a little more challenging. So the formula for us to be able to figure out the y coordinates for our Euler's method approximation going to be consistent as far as the method goes. And let's look for the pattern. What we're going to use here to find y1, we will use y0. So that is the previous y. And then we will have h, which is the step size, times, and then we got this f of x0, y0. So this will be the slope based on the previous xy. So notice how it's x0, y0 is used to find y1. So you're going to use the previous point to find the current point that you're actually trying to find. So that cycle will just continue. Then as far as how you're, maybe a way for you to remember this formula over here, I kind of remember it as sort of a slope-intercept. It's not exactly that, that of course slope-intercept form is y equals mx plus b. I kind of think of this as y equals b plus mx, where b is the previous y, m is the slope, so that matches, and then x would be the little tiny step size. It really is, we're just trying to find the, we're going to be using the equation of a little tiny line segment to try to match this up, and I'll show you a graph of this a little bit later that might make this a little more clear to you. So we're going to do one example, and then like I said, we'll look at a graph and hopefully tie it all together nicely. So let's go ahead and jump to example 1. So in example 1, we are given the information that we talked about earlier. We are given a differential equation and an initial condition and a step size. So we're given all three of those elements, and then we are asked to find or to estimate y of 0.2. So the way that I'm going to set this up is I'm going to set up my x's just like that little cycle that we looked at earlier. I'm going to start off with x0. x0 will be the x coordinate of my initial condition, so in this case it's just going to be 0. x1, that's going to be the previous x plus the step size. So my step size is 0.05, so x1 would be 0.05 plus 0, so it's just 0.05. x2 then would be the previous x plus another step size. So that would be 0.05 plus 0.05, which would be 0.1. So we're trying to get to 0.2. We're not there yet, but we can see that we're making progress. x3 would then be the previous x, which was 0.1, plus the step size. So now we are up to 0.15. And then finally, we're going to get to where we want to go with x4. It says 4 steps, so hopefully all this makes sense. We get to 0.2 when we have the step size under the previous x. So those are all your x's. Pretty easy to find. Just add the step size to get the next one. All right, so the y's. leave yourself a little more room for this. Y0 is going to be the y-coordinate of the initial condition, so that's 2. I'm getting that from right here. Okay, and so then we start kind of into this more challenging cycle here where y1 is going to be the previous y-coordinate, which is 2, plus the step size times the slope based on the previous point. So the slope is y prime equals x plus y, and so we are going to use that. So using the previous point, which is up here, x plus y would be 2 plus 0, which is 2. You add those numbers, add and multiply, correct order of operations, you end up with 2.1. Okay, so that's our second point on our approximation for our initial condition, 0.05, comma 2.1. All right, so then y2. This will equal the previous y-coordinate, which is 2.1, plus the step size times the slope based on the previous y-coordinate. So that would be the previous y-coordinate, the previous coordinates would be based on the ones, the x1, y1. Okay, so slope is x plus y. So based on the previous y-coordinate, it's going to, or the y and x coordinate is going to be 2.15. Okay, so again, that's y equals y-coordinate plus step size times slope. So kind of a b plus mx concept there. Okay, so you multiply and you add, you do all that stuff, you end up with 2.2075. Okay, we got 2 steps left. Hopefully this is making sense. So y3 is going to be based on the previous information, the most recent information. So the previous y-coordinate is 2.2075 plus now the, oh, I'm realizing that I wrote my step size wrong on those other ones. Let's fix that real quick. So that should be 0.05 and 0.05. There we go. Okay, so 0.05, and then the slope will be based on the most recent x and y coordinates. So the slope again is x plus y. So if I add 0.1 to 2.2075, I get 2.3075. So when I multiply and add all of that, I end up with a pretty big number here, or a pretty big decimal, I should say, 2.322875. Okay, and then our final step, y4, it's going to be the previous y-coordinate, which is 2.322875, plus the product of the step size times the slope based on the previous x and y coordinates. So when you add those two together, we end up with 2.472875. So we do our multiplication and our addition, and we end up with 2.44651875. Okay, so that means that y of 2, or y of 0.2, excuse me, is approximately equal to that number, 2.44651875. Okay, so down here below, I've made a little note that the particular solution to that differential equation is actually y equals negative x minus 1 plus 3e to the x. So in this chapter, we're actually going to learn where that came from. That's not part of the BC curriculum, but we're gonna talk about how you actually could solve that differential equation. Well, for now, what we're going to do is we're going to talk about how close we really were. So we're going to look at a graph to do that. So I've ahead of time prepared a graph that kind of illustrates this. So I'll switch screens here, and I want you to check this out. So keep in mind these points right here. So 0, 2, 0.05, 2.1, you know, the x2's and y2 there, 0.15, 2.322875, 0.2, and so on and so forth. So I'm going to have all those points listed on this graph along with the actual solution, which is right here. We'll compare those two. So check this out. So I made this graph on Desmos, and what you'll see over here on the left is the red graph is the particular solution, and then down below in all these other different colors, I've just listed out the various points that we generated with our Euler's method. So I'm going to do some zooming in. You can kind of see, I think, the points right there in the middle. Between x equals 0 and x equals 1. I'm going to zoom in a little bit. They look pretty good, don't they? They look like they're right on the graph. We're going to find that as we zoom in a little bit, they're not quite as perfect as we thought. Right about here at this level, we can see pretty clearly that, of course, 0, 2 is right on the graph. That was our initial condition, so that should not be a surprise. This green point, very close. Orange, you can see, is off, and the further we get away from our initial condition, the further off we are. If I keep zooming in, you can start to see that, yes, clearly we are off, this being our approximation. So the question in the notes was, how close are you? We're actually pretty close. I mean, you look at the scale over here, this is 2.45, so these are in, the little squares, at least on the y-axis, are in hundredths. So we're just, maybe about 2/100ths off the actual solution for y of 0.2. So I think at this point we could ask the question, how could our approximation be better? The answer is if we made our step size smaller. So if our step size was, instead of 0.05, was 0.01, it would take a lot more steps to get to 0.2, y of 0.2, but the approximation would be probably significantly better. So as far as what we would use, basically it comes down to a question of, well, how close do we want to be? We could make our step size larger or smaller accordingly. I hope this also looks like something, for those of you that are programmers, this is something that could very nicely be programmed into a computer or a calculator. It's very iterative, right? You just keep cycling through the same formula over and over, and a computer or a calculator could do that very quickly and generate a lot of points and a lot of data faster than we could do it by hand, of course. So, all right, so that is Euler's method. Hope that makes sense to you. We'll do some practicing with that. I see you in class next time.